Alright, so now we begin lesson 1 of our equations unit, and equations is saying, what if we give you things across the equals sign that make up an equation or a statement, and we have to algebraically manipulate to isolate for some given variable. Well, let's see if we can solve equations with a coefficient of plus minus 1 and see how this works here. So if we look at any given formula, well, it's a relationship of variables and numbers such that when we look at the left hand and the right hand side, we do operations over those left and right side such that we get a simplified statement in terms of variable on one and something on the other side. Now, operations are always done in opposites. So if I add, I subtract. If I subtract, I add. If I multiply, I divide. If I divide, I multiply. So let's take a look at the properties below here. Addition and subtraction. Well, if I add some number, then I can take something like a and b, which are a balanced equation, and add something to both sides. This keeps the equity across both sides, or makes sure that the equals is balanced across both sides. And I can do the same thing with subtraction if I wanted to. I could subtract the same value from both sides, and we know this is going to hold equality. Similarly with multiplication, we can take some original numbers, a and b, set them equal to each other, and if I multiply, well, if I multiply to the left, I must multiply to the right. We know the operation has to be done on both sides. And then finally, if I have a equals b and I want to divide, well, we know we have to divide both sides by one given value here. Let's say that's value c. It has to be done to both sides here. All right, so now let's talk about rearranging equations. To solve any certain variable, or to solve for any certain variable, it must be a positive value and be by itself or on the top. So if I look at some of the examples below, which one is correct in solving for x? Well, in the first case here, x equals 4, this is good because our x value is positive and in the numerator, and it's equal to some value. Perfect. If I go to my second example, well, 2x equals 6, this one still needs to be divided by 2 before it's an isolated term for x. 6 divided by 2 is 3. Now, we have a positive x value, it's in the numerator, and it's equal to some value. Perfect. The next example, x over 4 is equal to 7. This is a fractional term. We need to get that number out of the denominator. I have to do the opposite operation here. I'm going to take the 4 and multiply it to both sides, because we know if we multiply this number to both sides, it's going to be 4 divided by 4, which is just 1, or 1 times x, and that's equal to 7 times 4, which is 28. So our x value is alone, not fractional, and is positive. Now finally, or I guess we have a couple more examples here. If I look at negative x equals 14, well, I could approach this in two ways. One way would be, let me divide both sides by a negative 1. Because we know that the coefficient of any x term written as the following would be 1. So if I divide by negative 1, well, this then becomes positive x is equal to 14 divided by negative 1, which is negative 14. Or what we could do to both sides is say, what if we multiplied both sides by a negative 1? Well, this would give us the same thing, because a negative 1 times a negative x gives me positive x. And this is equal to a negative 1 times 14, that's negative 14. So you could approach it one of two ways. If you see that negative, you could multiply both sides by a negative or divide both sides by a negative. But I like to do the division because I know negative 1 times x, well, the opposite operation here is to divide by negative 1. So I think that makes the most sense to take this route. Now, in our final example here, we look at this and we see 1 over x equals 7. To get the x out of the denominator, without doing any complex exponent stuff, I'm going to take both sides and multiply them by x. When I do that, it eliminates the x's on the left here, because x over x is equal to 1. So I get 1 is equal to 7x. And now, if I have two things being multiplied together as follows, I'm going to divide by the 7, because it's the opposite operation of multiplication. And now I have x is equal to 1/7. Now this is something I'm going to bring up later in the lesson, but I originally moved my x from the left-hand side over to the right through operations, and now I had the x on the right-hand side, but then all of a sudden in my answer it was on the left. It won't matter if our final answer we have x on the left or right. As long as we've done the proper operations, we can exchange these across the equal sign, and this is a more common notation, is to have the variable on the left. So that's the only reason I swapped them back, but I will note this later in the lesson. All right. Now, What to do first? Here's a list of what to do first. Expand brackets, start with the term on the same side. So make sure you're dealing with the left side, then the right side, or the right side, then the left side. For adding and subtracting, we need to make sure that it's the same variable on each side. And we need to make sure that they cancel out, meaning we've done the opposite operations. Whatever you do to one side, you do to the other. Because we're undoing operations, we're doing the opposite operations. What you do to one side, you do to the other. And then finally, you'll just want to check your answer to make sure that the left-hand side equals the right-hand side. Now, this follows a lot of order of operations or just undoing operations in the proper manner. So let's look at the next page here. We want to keep things balanced across equal signs. So the whole point of doing things in terms of opposite operations is that we don't throw off the balance going on across an equal sign. What if I was to give you a statement such as the following? I have 2x plus 4 is equal to 7. Well, there must be some x value that makes this true, or else this statement wouldn't be possible. Well, if we do the correct operations, we should be able to solve for an x. But what happens if, let's say I have plus 4 here, and I think, oh, the opposite operation that gets rid of 4 is to add 4 to both sides. Well, then I'd be left with 2x is equal to 11, and then let's say I correctly divide both sides by 2, and this becomes x is equal to 5.5. Well, we would know this is wrong because I could go back into the original statement and plug this in. I would have, if I verify this, 2 times 5.5 plus 4, this should equal 7. Well, 2 times 5.5 is actually 11 plus 4 is equal to 7, and 11 plus 4 is 15. Which does not equal 7. So we know when we verify our solution, it said that it's not true. Why is it not true? Because we did something that threw off the equality here. If we do the incorrect operation, so for an example, if I have plus 4 and I go to move that plus 4 over, I actually have to minus 4, not add 4. Because if I add 4, it throws off the equality and whatever value I get isn't true. So think about this as a teeter-totter or keeping things balanced. We want the equality to always remain balanced as we do different operations. So in the example below, our teeter-totter, it's balanced here. What if we all of a sudden just throw 3 on one side? Well, we would know this would create an imbalance. So in order to add 3 to this statement, it must be done to both sides here. And then this keeps the balance here. So that's why when we do operations, they have to be not only the correct operation, but then be done to both sides. Okay, so let's take a look at some examples here. Solve each equation for the x, and then the key word is check here. We're going to have to look at our answer and say, is that actually true? Well, in my first example here, I'm going to rewrite x plus 6 is equal to 4 in my box, which is the original statement. To undo a plus 6 and isolate my variable, I have to subtract 6 from both sides, holding that equality. X is equal to 4 minus 6, which is negative 2. So supposedly negative 2 being plugged in for x will give this an equal statement or make sure that the left equals the right. But let's now check that. If we go to check it, we have to plug it in with brackets. Negative 2 plus 6 is equal to 4. We know a negative 2 plus 6 is equal to a positive 4. And therefore, if I can show this direct step or that they end up being equal to each other, I know I have the right answer. And there we go. We've verified or we've checked that x equals negative 2. All right, let's go over to example B. I'm going to do the same thing by rewriting the original statement in the box. If I want to isolate for x, I have to add 3 to both sides. So this becomes x is equal to negative 14 plus 3 is negative 11. So x supposedly equals negative 11, but let's check that. If I plug it in with brackets, negative 11 minus 3 is equal to negative 14. Negative 11 minus 3 definitely is negative 14. And therefore, because we could show that both sides are directly equal to each other, we know that this is a verified or a checked solution. Now make sure you don't stop at this step here. If you stop here, you haven't shown that the both sides are equal to each other because you're assuming that I would know that this is true, which in most cases, of course, I'm going to know that when you put this statement together, you'd probably get negative 14. But if you stop here, you're not getting marks on any assessment because you haven't clearly shown that the left equals the right. All right, and then now example C. Here's the big thing with C. I'm going to rewrite it as the original, but I want to note something right away. I have two constant terms on the left-hand side, and more specifically, I have a negative and a negative that become a positive. So when I go negative 21, it's going to be plus 3 plus x is equal to negative 15. I'm going to combine the like terms of negative 21 and 3, which give me negative 18 plus x is equal to negative 15. And now to undo the operation here, I'm going to go plus 18, effectively removing 18 from the left, isolating x as positive 3. Now, I want to double check this. I'm going to go back up to my original statement and plug that in for x. Negative 21, we knew that this became a positive 3. Then I have plus 3, which I'll throw in brackets. This is representative of the x. And this is equal to negative 15. Well, negative 21 plus 6, or plus a positive 6, this definitely does equal negative 15. And so because I can show that negative 15 equals negative 15, I've verified that x equals 3 is the solution here. All right, now for the u trisection here, let's quickly go through these. We won't have to verify them, we just want to algebraically show. X minus 15, I do the opposite operation here. And this is equal to, if I add 15 on the other side, I have to do it to both sides. X is equal to negative 19 plus 15 is negative 4. All right, I go over to B here. I have plus 23. Well, I have to subtract 23 from both sides to undo that operation that's being done to A, aka the plus 23. A is therefore equal to 40 minus 23, which is 17. Now, I go on to C here. C, I have a couple like terms here. I have 16 and I have negative 3. These can come together to make positive 13. So I go 13 plus h is equal to negative 24. Now I have to undo the operation that's happening here. Subtract 13 from both sides. Therefore, h is equal to negative 37. Okay, now there is two ways we could approach any given one of these problems here. Well, we could add the variable term across. In this case, we could add the variable term to both sides, eliminating the negative term. Or what we could do is we could say, what if we multiply or divide by the negative 1, getting rid of the negative 1 on the variable? And here's what we mean. Suppose I have the example below here, 15 minus x equals 20. Well, what if I moved the variable across to make it positive? Because we knew one of our things we wanted was a positive variable in our final solution. So what if I go plus x, remaining the equality here? This is 15 is equal to 20 plus x. And now I have this positive 20 that I'll subtract from both sides. 15 minus 20, x is equal to negative 5. And here's another example of this happening again. I isolated the x on the right-hand side, but then all of a sudden it appeared on the left. Here's where we're going to pause and make that note about earlier. An equation can either be where we have everything on the left-hand side, as follows with this example, or because it's equality, we can shift it to the opposite side of the equation, and just as long as all the terms are true, or they're the same terms as they were originally. So if I go between these two lines here, across the equality, the two amounts, or the things that are on the left and right, should stay the same. All they do is just swap positions across the equal sign. So they mean the exact same thing. These are the same. All they do is have the terms swapped from left to right. All right, so let's go to B here. B, 9 minus a equals negative 10. Well, let's solve it instead, isolating the negative a and then dividing or multiplying by that negative 1. Here's what I mean. Positive 9, I subtract 9 from both sides. Negative a is equal to negative 10 minus 9 is negative 19. And now I can either multiply or divide by the negative 1 to both sides. If I multiply both sides by negative 1, and I should probably rewrite the left-hand side here, or the right I should say, as multiplied by negative 1. If I multiply both sides by negative 1 here, I get a positive a on my left is equal to negative 19 times negative 1 is positive 19. All right, I go to C here. I realize I have two terms that are constant terms that can be collected together. I'm going to make sure I combine these. 32 is equal to 8 minus 16, which is negative 8 minus D. I'm going to add the D across to make it positive right away. So this becomes 32 plus D is equal to negative 8. Now, I'm going to subtract this negative 32 to both sides here because I know if I'm adding 32 on the left, I want to subtract to get rid of it, and I have to do this to both sides. Therefore, D is equal to negative 40. All right, now a quick you try section. Let's try these a couple more ways. So we have 7 minus x equals 12. I'm going to take this and I'm going to add x across. Add x across. This is 7 is equal to 12 plus x. Now, I have the positive x value, which is exactly what we want for our final solution, but I'm going to have to subtract a 12 from both sides because we know if it's being added on the right, I have to subtract it, and more specifically, subtract it from both sides. Therefore, x is equal to negative 5, or 7 minus 12. Now, here's another case of this. The x moved to the right, but then I put it on the left-hand side. This is totally fine. As long as we do the correct operations on the left and the right, in our final solution, we can state it however we would like, as either left to right or right to left, as long as we know that the operations have been done correctly. All right, in this example here, since we added the x across in that example, well, instead, let's isolate the negative a here. If I subtract 8 from both sides, this becomes negative a is equal to negative 40 minus 8. This is negative 48. And remember, the coefficient of any of these variables when it's not written, negative 1. So if I'm multiplying a negative 1 to a, well, I could multiply the negative 1 to both sides or divide the negative 1. Negative 1 times a, the opposite of multiplying is to divide. So I can go divided by negative 1, divided by negative 1. And therefore, this is a is equal to 48. All right, here's another example where we can collect like terms. The 12 and the negative 2 can come together. This is 32 is equal to 10 minus b. Now, I could add the variable across or wait till the end. What I'm going to do is I'm going to add the variable across, plus b, plus b. If it's being subtracted, I now add 32 plus b is equal to 10. And now I must subtract the 32 from both sides, therefore giving me b is equal to negative 22. Now, the nice part about all three of these examples, they do not say verify the equation. If they said verify, we would have to go back, take that value we got, let's say a equals 19 in the case of b, and we would have to plug it in for the original. But the nice thing is with here is they just want us to solve, so if you've correctly done all the operations and got some value at the end here, you know you've done all the correct steps. All right, this is where you get to check your understanding. There's a couple different worksheets. There's ones like these where you have to simplify and then the answer should pair across to some answer on the right. We have straight up worksheets where you just isolate the variable and then another worksheet to follow. Get your practice.